In example one, we're given dy dx as x times y, and we're also given a slope field over on the right-hand side. Part A describes the slopes, or is asking us to describe the slopes of the tangent lines in each quadrant. Let's take a look at each individual quadrant, and I'll remind you guys which quadrants those are. So this is Q1, and this is Q2. We usually use Roman numerals for that. And then over here, we've got Q3. And finally, bottom right-hand side, this is going to be quadrant 4. So if we look at quadrant 1, all the slopes appear to be positive. We've got a positive line right here, a positive slope, a positive slope, and even these ones are positive. They're just pretty high in number. So we're going to list Q1 as having a positive slope. And if we take a look at Q3, in Q3, those slopes are also positive as well. So we can list Q1 and Q3, or quadrants 1 and quadrant 3. So we'll do this here. It says describe the slopes. Q1 and Q3 have positive slopes. And let's think about the other quadrants. So we've got quadrant 2. So we have a negative slope here, negative slope here, negative slope, negative slope. In quadrant 4, we have the same situation happening. As a matter of fact, we've got negative slope here, negative slope here, negative slope here. So it appears that also in quadrant 4, we have some negative slopes. So we'll write Q2 and Q4. The slopes are negative. Part B says using 3 different colored pencils, sketch 3 possible solution curves to this differential equation. So I'm going to try to get rid of a few things on the graph so we can focus on that now that we know where the quadrants are. We'll get rid of some of these slopes over here. And then we'll draw some solution curves. Now, solution curves, you have to match them up with the slopes of the tangent lines, but we also want to pick a point or two just a point to draw that in to start with. So what I'm going to do here is I'm going to arbitrarily just pick this point right here. And what I want to do then is I want to try to draw a curve that matches these tangent line slopes. And as I do that, I wind up with something that looks a little bit like this. I'm going to choose a different color now, and we'll go with another possible solution curve. And you can pick whatever point you want. I'm just arbitrarily going to pick this point right here, and we're going to try to draw a curve that matches all of those tangent lines as well. So we're seeing a couple things happen. Oops, that kind of caught that line in a little bit too tight there. So we'll try that again. Draw a nice line here. We'll try to match that up. These guys are a little bit off right here. Ideally, I should have a little bit more vertical piece right here, as those tangent lines are a little bit more vertical. So I might have to draw something that looks a little more like this, but just try to do the best job that you can. And then in another color here, we'll maybe pick something below the x-axis. So just arbitrarily again, you can just pick whatever point you want. And then we'll try to draw a solution curve where those little tangent lines are tangent as well. That was a little wobbly. Interesting trying to draw with the stylus here. So then we'll draw something that looks like this. Now they all look pretty similar to each other. They're, well, actually in part C, it says describe the general shape of a solution curve. So maybe we should do that there. Couple bullet points here. So we could say that maybe they look kind of parabolic. Now, that doesn't mean that it's a quadratic solution to the differential equation. That's just the shape of the graph. Kind of looks parabolic. We can also say that if we look at a graph here, that from the red and the blue graph, they look like they're just kind of vertical shifts of each other. So we could say that they're maybe shifted vertically. And another thing we could say is that the vertex, and we could say shifted vertically or reflected. How about that? Because the green one right there that you can see is also reflected. And then we could also say that the vertex appears to be on the y-axis, wherever that is. So these are good things to notice about the solutions, and that can kind of help us sometimes figure out a particular solution, which we'll do in the next lesson. How do the solution curves differ? Why do you think that is? So we could say here also that they're different because they appear to be vertical shifts from each other. So we could say they could be shifted vertically, kind of like what we noticed before. And also, let's see, why do you think that is? Let's do that too. So it says shifted vertically, and we could say we don't know the value of C. So remember, when you're finding that antiderivative, you'll have that value of C hanging out, and that value of C represents a vertical shift. And we don't know what that is for this. We don't have a particular solution. We don't know exactly which point or points that one goes through. Also, how are they different? Some are reflections. So we could say some are reflected. And this means there could be a plus or minus coefficient as maybe a leading coefficient for this. So that'll happen when you have it both a positive and negative. You'll have both above the y-axis, and then some solutions will be below. So we're kind of expecting that, and we're going to hit this up again in a different example. We're going to show you analytically using algebra why that actually happens.